Hello everybody. Today I shall be talking about my pattern recognition project on finger vein pattern matching based on line tracking for user authentication under Dr. Depengu. Coming to motivation and introduction, we know that nowadays fraud cases and thefts have become common. Thus, a strong and reliable security system to identify the legitimate individual has become indispensable in areas such as PC login, internet banking, and the like. Conventional methods such as using passcodes, PIN numbers to identify the authentic user has its limitations in terms of relying on an individual's memory loss or theft. Hence, personal identification based on biometrics, which is the identification based on measuring an individual's physiological or behavioral characteristics, is more reliable since these features are unique to a particular individual. In this project, a biometric system was designed in which personal identification was carried out based on an individual's vein patterns inside his or her finger. The brief description of the methodology used has been given in the next slide. A brief outline of the methodology is as follows. First, the hand is placed in between infrared light on its back end and a camera on the front end. Infrared light is passed through the hand, which is absorbed by hemoglobin, and the image of the vein pattern on the palm is then taken using the camera. The image contains shadowy patterns of both veins as well as irregular noise and shading due to dissimilar thicknesses of muscles and bones. Hence, to obtain a clear image of the veins for reliable personal identification, very precise extraction of these vein patterns is a must. In this project, extraction was done using line tracking starting at different positions. In this method, tracking of all the dark lines in the image was done by repeatedly carrying out local line tracking operations. The loci of the lines overlap, following which the pattern of the veins is statistically obtained. As this tracking of the dark lines is repeated several times, the patterns become increasingly prominent. Noise is also tracked but is less prominent than the dark lines, thus making line extraction very powerful. Furthermore, computational costs can be lowered by decreasing the tracking operations and spatially reducing the pattern. Coming to the diagrammatic representation of personal identification of finger vein pattern. The figure on the slide shows the principle of personal identification using finger vein patterns. The detailed steps are described on the next slide. The procedure for personal identification by using patterns of veins in a finger is shown in the figure on the left. It is divided into 5 steps as can be seen. It is the acquisition of infrared image of the finger. A special imaging device is used to obtain the infrared image of the finger as shown in figure A on the right. Figure B and C are examples of the captured images. Normalization of the image is given as the location and angle of the finger in the image require some form of normalization, since these qualities will vary each time. Two-dimensional normalization is done using the outline of the finger on the assumption that the three-dimensional location and angle of the finger are constant. Extraction of finger vein patterns. The finger vein pattern is extracted from the normalized infrared image of the finger. Matching. The correlations between the input pattern and all the registered patterns are calculated. Output of the result of identification. When the pattern is identified as a registered pattern, the required action such as unlocking a door or logging onto a PC is performed. For robust extraction of the finger vein patterns from the non-uniform images, repeated tracking of dark lines in the images was implemented in this project. Extraction of the patterns was based on the number of times the tracking lines was passed through the points. First, we have the repeated trials of dark line tracking. A cross-sectional profile of a vein appears as a valley as shown in figure A. The depth of the valley varies with the shading in the image. However, the valley remains detectable. Therefore, the profiles give us a robust method of finger vein detection. The current tracking point is moved pixel by pixel along the dark line. The depth of the cross-sectional profile is checked around the current tracking point. The second figure below on this slide shows an example of the spatial relationship between the current tracking point and the cross-sectional profile. Pixel P is a neighbor of the current tracking point in the upper right direction. Cross-sectional profile's SPT looks like a valley. Therefore, the current tracking point is on dark line. The direction of this dark line can be detected by checking the depth of the valley with varying theta I. If only a single line tracking operation is conducted, only a part of veins within the image will be tracked. To solve this problem, vein tracking sequences are started at various positions that are determined so that the line tracking trials are conducted evenly across the image. The current tracking point may track a region of noise by chance. Statistically, however, the dark lines are increasingly tracked more often with repeated operations. This makes for the robust extraction of pattern of the finger veins. The positions with high values in the locus space have high probabilities of being the positions of veins. Therefore, the paths of finger veins are obtained as chains of high value positions in the locus space. Coming to algorithms, the first stage is feature extraction. F of xy is the intensity of the pixel xy, xc, yc is the position of the current tracking point of line tracking in the image. Rf is the set of pixels within the finger's outline and tr is the locus space. Suppose the pixel in the lower left in the image to be 0, 0. The positive direction of the x-axis to be rightward in the image, the positive direction of the y-axis to be upward within the image, tr of xy to be initialized to 0. The steps are as given below. The starting point for line tracking is XS, YS, a pair of uniform random numbers selected from RF. That is, the initial value of the current tracking point XC, YC is XS, YS. After that, the moving direction attribute DIR and DUD is determined. DIR and DUD are the parameters that prevent the tracking point from following a path with excessive curvature. These two can be determined as follows. Detection of dark line direction and movement of the tracking point. This step is composed of several sub-steps. Firstly, the position that the tracking point moves to are stored in the locus position table TC. The table is initialized in this step. Secondly, a pixel to which the current tracking point XC, YC moves must be within the finger region. Have not been previous XC, YC within the current round of tracking and be of the neighboring pixels of XC, YC. Therefore, NC is determined as can be seen. Detection of the dark line direction near the current tracking point. To determine the pixel to which the current tracking point XC, YC should move, the following equation referred to as the line evaluation function is calculated. This reflects the depth of the valleys in the cross-sectional profiles around the current tracking point. Registration of the locus in the locus position table TC and moving of the tracking point. The current tracking point XC/YC is added to the locus position table TC. After that, if VL is positive, XC/YC is then updated to XI/YI where VL is maximum. Repeated execution of steps 2, 2, 2, 2, 4. If VL is positive, go to step 2. If VL is negative or 0, leave step 2 and go to step 3. Since XC/YC is not on the dark line, updating the number of times points in the locus space have been tracked. Values of elements in the locus space Tr of x, y are incremented for every xy belongs to Tc. Repeated executions of step 1 through 3 for n times. If number of repetitions of n is too small, insufficient feature extraction is performed. If, on the other hand, n is too big, computational costs are needlessly increased. Through an experiment, we determined that n for 3000 is the lower limit for sufficient feature extraction. Acquisition of pattern veins from locus space. The total number of times pixel x, y has been the current tracking point in the repetitive line tracking operation is stored in the locus space Tr of x, y. Therefore, the finger vein is obtained as chains of high values of Tr of x, y. After feature extraction, the next step in the algorithm is matching. In the matching process, the pattern is converted into matching data and these data are compared with recorded data. Two methods are commonly used for matching line-shaped patterns, structural matching and template matching. Structural matching requires additional extraction of feature points such as line endings and bifurcations. The ambiguous regions around the vein are identified and the slight misalignments between vein patterns in these regions are ignored. Robust template matching is thereby achieved. The matching process is as follows. Labeling of the locus space. The locus space is binarized using a threshold. Pixels with values smaller than the threshold are labeled as parts of the background, and those with values greater than or equal to the threshold are labeled as parts of the vein region. Here, we define the values of pixel labeled as parts of the background as 0 and of pixels labeled as parts of vein regions as 255. Spatial reduction and relabeling of the locus space. To create matching data, spatial reduction and relabeling of locus space are performed. In order to retain veins as small as about 3 pixels in the image, the locus space is reduced to 1/3 of its original size in both dimensions. In this study, pixel values in the range 0 to 885 are converted to 0, which represents the background region. Pixel values in the range 86 to 170 are converted to 128, which represents the ambiguous regions, and pixel values in the range 171 to 255 are converted to 255, which represents the veins. The value of mismatch Nm of S, T, which is the difference between the registered and input data at the positions where R of CW, CH overlaps with I of S, T is defined as can be seen in equation 7. When P1 is defined as pixel value of 1 pixel and P2 as other, phi can be described as can be seen in equation 8. The minimum value of mismatch Nm, which is smallest, calculated under the condition that the template overlaps with the input matching data I of x, y at all positions, can be defined as can be seen in equation 9. Using the definitions given above, the mismatch ratio Rm is defined as can be seen in equation 10. Rest of the project presentation is seen in second video.